Hello everyone. In this video, we are going to cover A2 and we are going to cover uniform circular motion of this A2. So in the previous videos, we have covered the forces part, Newton laws part of this chapter. And in this video, we are going to see how the circular motion is going to combine with forces and also gives us how to apply Newton's law to this circular motion and some basics of angular motion, angular displacements as well. Now, if we look at our uh, guide, as per the syllabus guide, we can see that we need to know what are the circular trajectories at a constant speed and how those formulas of centripetal acceleration, centripetal force are used, along with some basic definitions of angular displacement, angular velocity. Okay, so starting with uniform circular motion, let's first define few important terms. So we know what is a linear displacement, but in case of circular motion, if I want to define a displacement, then uh, along a circular path, if this is the line, if I draw, then this is the length of an arc of an object, and if I take this length, then this will be a linear displacement. Okay, so it is not the shortest point distance between A to B. So, but I'm considering very small distances. So this will be if I reduce this theta for very small angles, then we can have that as a displacement. But now we are going to talk about the length of an arc as a S, what I represent in the circular motion. Okay, along with that, the angle traced by this object uh, following the arc will give you the angular displacement. Okay, so angular displacement is between 2 points, how much angle is traced up while moving around a circle. And we know from basic math what is the relationship between length of arc and the angular displacement. And this is given by this relationship S is equal to r theta, where r is the radius of the circle. A theta is the angle, but it must be in radians, and s is the length of an arc. Okay, so basic radians to degrees conversion is necessary in this chapter, uh, because every quantity, angular displacement, angular velocity, whenever we are looking at angular, it has to have units of radians. That's the basic SI unit. Okay, and we know, like, if I give you angle, any angle in particular, for example, in terms of theta as a degree, we can convert that by multiplying pi by 180 to get it in some radians. Okay, so that is the basic conversion that we have. What is the definition of a radian? A radian is angle when the angular displacement is such that the body moves the length of an arc equivalent to the radius of the circle. That's the definition of radians. Okay, circumference, basic formulas for circumference is also should be known. So we can calculate the circle. If you are moving around a circle, uh, how much will be the total distance? That will be a circumference. So moving around a circle is also called as revolutions. Okay. So the next quantity we are going to talk about is linear velocity. So in this case, linear velocity is the rate of change of displacement. That is something that we already know. But in circular motion, this velocity is always tangential to the circular path. We have to remember this. No matter at which position, it will be always be tangential. So you can see that it always makes an angle of 90 degrees with the radius of the circle. So this is the sometimes this is also called as tangential velocity. Okay, and whenever we are dealing with the magnitudes only, we can say this is a linear speed or tangential speed. Okay, because direction is sometimes in circular motion it is very obvious, because if it is moving in circle, in whatever direction, it will be always be tangential, and this is very necessary. For example, if this is a string and I am spinning something like an object uh, at this mass, okay, and if I cut this string, so whenever at whichever position I cut the string, the object will follow the straight path as per the tangential velocity. Okay, so if I cut the string here at this position, the object will go in that direction. So this is very important so that we know that what will be the direction of the tangential velocity. Then we have our angular velocity. So angular velocity is rate of change of angular displacement. So this is a new introduction. So angular displacement we already see. So it has a unit of radians per second, and it is also a vector quantity. Uh, so you can see that if the object is rotating in a plane, the angular velocity will be 90 degrees, and we can use a thumb rule to predict the direction of the angular velocity based on the rotation. So if I have my thumbs uh, giving me the direction of angular velocity, then you can see our fingers are going in the direction of the rotation. So, so this is a basic thumb rule that we can use to predict the direction of the angular velocity, but it is always 90 degrees or normal to the plane of rotation. Now, angular displacement, angular velocities are sometimes simplified in this particular chapter by giving you the angular displacement to be equal to 2 pi, that is 360 degrees. Okay, that is one full rotation. So if the angular displacement is one full rotation, then it will be 2 pi, and the time taken to complete one rotation is time period. So we can define this as time taken to complete one rotation. Okay, so if we take those two values, then we will get our angular displacement to be equal to 2 pi by capital T, where capital T represents time period of the rotation. Okay, uh, then we have one more quantity like frequency. Frequency is defined as number of revolutions completed per second. So we can have the frequency given in hertz. So for example, if I have 10 hertz, it means 10 revolutions are completed in 1 second. And there is a sometimes you will find questions instead of giving you in hertz, they will give you frequency in terms of RPM, that is revolution per minute. So you can convert revolutions per minute uh, by multiplying by 60. So you can see that one revolution is two, and then we can have the angular displacement as well. Uh, so one revolution is 2 pi. Okay. So for example, if I want omega in terms of radians per second and I have RPM, so what I can do, one revolution is 2 pi radians and 1 minute is 60 seconds. So I will get my answer in radians per second like this. Okay, so we can convert, those conversions are necessary, okay, before substitution in formula. And since frequency is equal to 1 over time period, we can also get the another formula for omega as 2 pi by f, 2 pi into f. So omega has, we can see it has couple of formulas. So it has angular displacement over time, it has 2 pi by time period, it can be also written as 2 pi f. So sometimes this omega is also referred as angular frequency. So whenever they say angular frequency, we can take this as a unit. Then once we get through this, we want to relate linear speed with the angular speed, and this is very simple in that case. So we know the basic definitions of both these quantities, okay, and we know the relationship between linear displacement and the angular displacement by the length of the arc formula. So you can see this, the length of the arc formula is s is equal to r theta. So delta s should be equal to r delta theta, and if I divide this both by time, I will get a relationship that the linear speed is equal to r omega. So r is the radius of the circle. What does that mean? For constant omega, okay, that is most important for a constant omega, because whenever it is tracing a circle, the omega will be same for both these points. Okay, if they have the same omega. For a constant omega, we can say that the greater the distance from the center of the rotation, the faster is the revolution of the body. So this is very simple, but very like problems are asked on this particular section where we need to relate the distance and the linear speed. So this linear speed changes with the distance, while angular speed can remain constant. Okay, so this is the case in this particular relationship. So these relationships are important. We need to remember those relationships. You will also find that this V is sometimes referred as like R omega, but we know that omega is uh, 2 pi by t, and this becomes like velocity is like angular like total displacement over time period. So if I have like circular motion, the entire distance covered is like 2 pi r, and the time taken is time period. So we can relate both this quantity with this relationship as well, or omega can be also be written as 2 pi f. So all those relationships become valid. Okay. So then we have another thing, like whenever object perform a circular motion, there is a chances that it will have a centripetal acceleration in most of the cases, because even if the object have a constant speed, there will be still be a acceleration towards the center. Now, why is that? Because even if so, uh, acceleration is defined as rate of change of velocity, and velocity being a vector quantity, it has two things. It has direction. Important that the change in direction of the velocity causes the acceleration that we call as centripetal acceleration. Okay, so even the change in direction of the velocity, keeping the magnitude constant, can lead us to acceleration. So even if you see that the speed being a magnitude, speed is same throughout the circular motion, but there is some kind of centripetal acceleration. So keeping the magnitude same, we can have the acceleration. Okay. Now, how do we calculate this acceleration? Why this acceleration is always toward the center? We will try to explore that. So, for example, if I consider these point A and B, okay, throughout this motion, you will find that if I want to find a change in velocity vector, it will be velocity B minus velocity A, and these are vector quantities, so they won't subtract or add in a normal way. So we need to draw a vector diagram. So let's say B is like this. Okay. Now A is negative A, so we can write this as VB plus minus VA. Minus VA from this point will be like this, exactly in the opposite direction of what is the VA. Okay. And then if I take a resultant of it, this will give me change in velocity vector. Now this change in velocity vector, if I draw it from the center, you will find that this is always towards the center. And you can pick any 2 points on the circle, take two velocities and try to find the change in velocity vector. You will always find a change in velocity starting from the middle of the length of the arc. You will always find to be pointing towards the center. So this is the reason why there is a centripetal acceleration, because the acceleration is in direction of the change in velocity. Okay, so this is how we can say that whenever there is a velocity doing a circular motion, you will find that there will be a centripetal acceleration pointing towards the center of the circular path. Then, if we want to calculate how much how we can measure this, okay, apart from knowing the direction. So, like a length of an arc, imagine for very small theta, we have two velocities, u and v. Okay, now u and v are same velocities magnitude, but their directions are different. Okay, uh, so like a length of an arc, this represents the change in velocity vector. Okay, if we resolve the vector, this is v minus u. Okay, the reason why this will be like this. So you can use a triangle law where u and delta u are making a triangle and the third side is completing the resultant. So using a triangle law, we can get this, and using the length of an arc relationship, we can get a relationship between the change in velocity and angular displacement. Now, derivation of this angular centripetal acceleration is not expected in the syllabus. It is just for your knowledge. So try to remember, we are understanding here. This derivation is not going to be asked in the exam. Okay, so we get this. If we divide it by time, we get the relationship between the acceleration and the linear and angular velocity. Okay, so this is something that is the outcome of this, but we can the most commonly used is like we know that v is equal to r omega, so we can replace the v and we will get a centripetal acceleration to be equal to r omega square, and we can replace omega as well, and we will get centripetal acceleration as v square by r. Now this is the most commonly used. Okay, now here one more equation you will find in the data booklet is that if I replace omega by 2 pi by t whole square, the for this A is equal to r omega square, you will get this as 4 pi square r over t square as a relationship. So these are all commonly used, okay, and all formulas are related to one another, okay, but these are centripetal acceleration. So whenever an object is performing a circular motion, this acceleration is there, and the force that uh, is outcome of this acceleration is what we call as centripetal force. Now, centripetal force is most important. We have to remember it is a resultant force. The resultant force that carries an object to move in a circle about. So it is not just one force. Why resultant? I'm talking about. It is not a new force like a tension or like normal force. Like it is not a category of a force. It is a resultant force in itself. Okay. So resultant force is always in the direction of the acceleration. Okay, so no matter you have, there are multiple forces acting on an object, there is only one resultant acceleration for the object, and one resultant acceleration is always in the direction of resultant force. Okay, so this is a resultant force. So we need to know that centripetal force is not a new force. It is rather the existing forces combined in a way that the resultant of them is always pointing towards the center. I will try to repeat this. Centripetal force is not any new force. It is the existing force combining in a way that the resultant of those existing forces points towards the center. Okay, so this is something that we need to know. And centripetal force comes first, and the resultant force, other forces align themselves at their magnitudes such that the resultant forces towards the center. Okay, we will see the example of this. So, for example, if I have a pendulum and it is at rest, the forces are balanced in this case, and that is true. So the tension will be 100 Newton upward, weight will be 100 Newton downwards. But what if this pendulum is performing a circular motion? Then it is not in equilibrium. It is never in equilibrium. Why? Because the tension has to be greater than the weight at all times. Uh, at least at the bottom part of this journey. Okay, so that we can say that the uh, net force is tension minus the weight, and this net force is centripetal force. So this net force can be replaced by mv square by r. That is the formula for centripetal force, and we get this type of a relationship. So whatever we forces we have learned in the first part of this video, uh, we will see that the net force coming, the Newton's laws are coming in, okay, as normal as it can, but we will replace the acceleration wherever we are substituting net force is equal to mass time acceleration. I will substitute the acceleration as v square by r or r omega square in case of circular motion. So everything is same. We just have to be aware that if the object is performing a circular motion, that there has to be a resultant force pointing towards the center. Okay. So for example, there are some like planets rotating. Okay. In planets rotating, planetary motion, orbital motion, like a moon orbiting our Earth, the gravitation is the centripetal force. Electron moving around a proton in an atom, electric force, electrostatic force is the centripetal force. A car taking a turn on a like a road, which is so friction is playing us. Friction will be pointing towards the center, and that will be a centripetal force. Okay. If I have a water in a bucket and I'm swinging it, okay, about a circle, in that case, the contact force of the water with the bucket is the centripetal force. So there are multiple cases. We have multiple examples when we see problems. We will see that there are multiple possibilities, but no matter how many forces are acting, the resultant force is what gives us the centripetal force. Okay. So one example is this object moving in a horizontal circle with a thread attached to it. So you can see that there is a thread attached to a ball of mass m, and obviously in the direction of the thread there will be a tension force and weight will be pointing downwards. Now you can see that there is no actual force towards the center, but still this object is performing a circular motion. So to understand this, what we do, we break down the component of the tension force into vertical and horizontal component. Okay, and we have to understand that if the object is performing circular motion, the acceleration will be towards the center. It means that the vertical acceleration has to be zero and the vertical forces are balancing itself. So the W cos theta is balanced by the weight. Okay. Sorry, T cos theta is balanced by the weight. And the T sin theta here is not balanced by any other forces. So we can say that the T sin theta acts as a centripetal force. We can equate with this and we can get a relationship like this. So we need to understand that we need not to have a like a force. A centripetal force is not an actual force, but rather than it is a combination of other forces, existing forces, such that the resultant is pointing towards the center of the circle. Okay, and we are just replacing the centripetal formula with mass time acceleration. That is, net force is equal to mass time acceleration, and acceleration we are replacing with v square by r or r omega square. Okay, we will see another case here. Another possibility is that is it possible to for the object to move in a pure horizontal circle? It is not possible because obviously there are two forces. So we have to always check this. This is always kind of a question they ask in the exam as well. Like if you have this kind of a setup, is there a horizontal circular motion possible? Then you have to say it is not possible because the resultant of these two forces is like this. So acceleration will be in like this. Acceleration, if it is not pointing towards the center, then it won't be any circular motion anymore. This object will like go downwards spirally. Okay, like this. Okay, so we need to have the vertical component at least some, so that we can balance the weight here. So this is where we need to have that knowledge where the resultant force has to point towards the center. Okay, I have one more case here. Object moving in vertical circle. So in object moving in vertical circle, we can see that there are if the tension here is a centripetal force, but along with the weight as well. So if the object has a weight at different position, we will find that the resultant force changes, okay, in vertical circular motion as per the gravity. So you can see that at position 1, the resultant force is tension minus weight, because weight is opposite. The net acceleration has to be towards the center. So resultant forces, this acceleration can be replaced by mv squared by r. Okay. At this point, a random point, we can see that the weight is this, tension is this. So if we take the component of the weight w cos theta, the resultant forces like this. Okay, t minus w cos t. Then uh, the resultant force at point 3 is just tension pointing toward the center. Okay, and then at the top you can see that the tension plus the weight is equal to mass time acceleration. Now here you can see that the tension is centripetal force minus weight. So tension will be least at the point 4. Okay, and it will be the maximum at this point 1. The tension will be maximum at this point 1 because centripetal force will be added with the weight. You can see the equations. Okay, so this is the case of vertical circular motion as well. Okay, we'll see an example where what will be the minimum speed, because here you can see that the resultant of these two is not towards the center, correct? So because of this kind of a change in vertical circular motion, the one thing that we need to address here is that the velocity is magnitude wise. Okay, the magnitude of velocity is changing throughout the motion. So at the top the velocity will be different, at bottom the velocities will be different. So that's the case we need to remember. And if by chance if you have a vertical circular motion with a let's say a rod or something like that, which is very stiff, and we are forcefully rotating this object at a constant speed, okay, at say all the points, in that case the tension won't be towards the center, but on this rod it will be at any some other point, like let's say the weight is downwards for a rod instead of string. For a rod, the tension will be somewhere in the force exerted by the ball on the rod will be somewhere like this, so that the resultant force of these two points towards the center. Okay, so this is the case with the rod. So we have to be aware that the resultant force will be towards the center if we are maintaining a constant speed. If we are not maintaining constant speed, then the resultant force, uh, we can break down the forces along the center and we can take the centripetal acceleration as the centripetal force. Okay, only centripetal. So it will have some vertical acceleration also, tangential acceleration also, because of gravity in vertical circular motion. But that is the part that nobody is going to ask question to you. Basic things that we need to remember is that in vertical circular motion, the velocity is changing. So we will always only think about the forces that are pointing towards the center, the resultant forces that are pointing towards the center. That's the acceleration. That's the direction that matters to us. In case of if you are maintaining constant speed in vertical circular motion, the tension is not going to be towards the center along the rod or something like that. And it is possible with the rod only, because string usually bends if you are trying to maintain a constant speed with them. So if it is a rod that is sticking, then there has to be some tension that will be pointing in a direction such that the resultant will be always towards the center. Okay, so these are the minor things. Now speed at so most of the time they ask a question where the object is performing a circular motion, what is the minimum speed at the top, so that the object do not or the string do not get slack or if it is a normal force like a roller coaster you are going, what is the minimum speed at the top of the coaster so that you can do this motion, okay, without falling. So this kind of a stuff is asked. So where we can take that the net force in this case is tension and weight in the same direction. We can take this equal to mass time acceleration. Okay, here it will be normal force plus the weight will be equal to the centripetal force. Okay, and we get this kind of a relationship. So here we can say that for the minimum speed of rotation, the tension has to be greater than or equal to zero. Okay, because if it becomes less, the tension becomes zero or less than zero. Anything less than zero, basically the string will get loose. Okay, and an object will fall. Or even in here, the normal force has to be greater than equal to zero. So if it is a normal force becomes zero, you will lose a contact. Okay, it can't become negative. So we can take to find the minimum value of speed, we can take the tension or the normal force to be zero in this equation, and from this equation we can get the relationship between the minimum velocity. So minimum velocity at rotation at the top of the circle in vertical circular motion is given as v is equal to root rg. And here, if I want to calculate, if I know this is my radius and it will be 2r, the diameter. If I want to calculate what is the velocity at the bottom, if the velocity at the top is root rg, then I can use conservation of momentum between this point A and point B. So at point A, it has mg2r, that is the height, gravitation potential energy, plus it has half mv square. So v square is the kinetic energy at A. Similarly, at B, it will only have kinetic energy. So we can calculate this velocity using conservation of energy in circular motion. So this is the minimum velocity at the bottom so that it can go with that velocity at the top. Okay. So if we substitute this VA, that is root RG, we will get half mgr, and this will be half mvb square. So we can cancel out all the m's. Okay. And if we work out the math, we will get the relationship that Vv will be equal to phi g root of phi gr. So this is the velocity, minimum velocity uh, at the bottom, so that the object can perform a vertical circular motion without the string getting loose or the normal force becoming zero. Okay, so this is what we have covered in this circular motion. In next video, we are going to talk about momentum. Okay, so thank you so much.